Thank you very much. Merci beaucoup, Christophe. Et merci à David aussi de l'invitation. Thank you, both of you. Concerning the format, I'm going to speak in English, and then when I'm done after the 50 minutes, I'm going to give the same talk in French for another 50 minutes. I hope it's okay. No, I mean, thank you very much, Christophe, for both, but I'll stick to the German, the English part. Sorry. So briefly, the outline, which does not work. Okay. Yes, I'll briefly present the German Aerospace Center. And then what's very important to me is always to present the methods and tools and try to give some details. But I think at any stage in your, as a student or later on in your career, you should always put what you do in a bigger context, try to understand the problem. So that's what I'm going to do with the second two bullet points, with trying to describe the climate and environmental impact of aviation, and then define what is SAF, Sustainable Aviation Fuel. And once we have this context, I'll try to present the methods and tools that we're using, and then give a broader view about this multi-scale, multi-physics problem. And you'll see different aspects. And at the end, I'll touch upon the fuel design and then some real-world application. So, as I said, very brief introduction of the German Aerospace Center. Historically, the main focuses were, as defined in the name, in the title, aeronautics and space research. And then later came also the two additional topics, which are energy and then transport as a wide, more than just aeronautics. And I think this is quite important here in this context, because SAF, so Sustainable Aviation Fuel, has really a foot in those two main areas, which are aeronautics and energy. We also have some dedicated institutes and application in security, and now we started also in digitalization. It is Europe's largest research center for aeronautics and space, and as many, almost all research institutions, we have corporations with other sectors such as business and industry. And we're funded by many German ministries. In the title, you can read, it has 10,000 employees and across 55 institutes and 30 sites in Germany. So I originally come from France, and in France, there are many things that are centralized. So it's quite interesting here to see this very different organization where it's spread really all across the Bundesrepublik in Germany. So it's a nice structures. Now, specifically on the institute where I work, the Institute of Combustion Technology, it's VT in German. And I like this picture here to present the institute, because it really shows that we're trying to span the bridge between fundamental science and the fundamental understanding of the different fuels, the chemistry of the fuels, the properties. We have a very strong department on diagnostics, and then CFD and different methods. And then we go gradually to larger, more complex systems than just lab scale experiments, where you can test all the different aspects under realistic conditions, high pressure, high mass flows, and finally the whole system. And then we try to assess the impact of what has been developed in terms of climate and environmental impact. So again, this whole bridge from fundamental science to technology. Okay, now I'd like to set the scene a little bit and describe what's the challenge. You have this challenge of maintaining a social and economic benefits of aviation while reaching climate neutrality. So on the one hand, here for 2019, you see that, yes, there's been almost a billion tons of CO2 that's been produced by aviation, commercial aviation, which sounds a lot, but it's not much compared to the 40 billion tons of CO2 that were produced during that year. So it's only 2.4% of the so-called anthropogenic CO2 emissions. However, if you put this into the perspective of aviation represents 12% of all transport sources, and 80% of aviation CO2 stems from flights that cover more than 1,500 kilometers. So this is hard to find an alternative if you're thinking of a road transport. And then the whole aspect of the business and the economics behind it. So it's not that easy to just stop. Obviously, it is the easiest way to really make an impact. It's to not to travel, but it's not that easy. So what's the goal? The goal that was set in many countries, many continents, is really to reach climate neutrality by 2050. So in Europe, it's actually a law. And so you see this plot here on the right-hand side. You will see it very often if you're interested in that topic, and very often it is an artistic view. Here at the DLR, a large study was performed to derive different scenarios. So different types of aviation transports with different technologies, different levels of maturities, and then two scenarios. One, the so-called conservative, and another one, the so-called progressive scenario. So if you see here, I won't go into all the details, but basically the gray plot shows business as usual. We don't do anything, and this is how the CO2 emissions will grow in the coming years, all the way until 2050. If you start improving the technology as has been, since 1950, there's about 1.8% fuel reduction per year that has been achieved by the aeronautics industry. It's extraordinary. It's really if you look, every 20 years, it's more than 23%. So it's really great, but that will definitely not be enough. So if you look at a progressive scenario where you really pushing to the maximum the technological improvements, you'll get this green line. So it's good, but it's far from inversing that trend. And this is what we want for 2050. If we really want to reach climate neutrality by 2050, you need to inverse that trend. And you see here with the progressive scenario, the only way is to add SAF, sustainable aviation fuel. So which means a fuel that reduces the CO2 emissions from a life cycle perspective. And I'll try to explain this. Now, in aviation, there's a second aspect. This is a little complex, but it is very, very important to know about it. That CO2 emissions are not the only contribution to the climate impact or climate forcing. There are also so-called non-CO2 effects. And where do they come from? Here on the right-hand side, you see often in the skies contrails being produced or emitted in the wake of a civil aircraft. And under very specific conditions in terms of humidity and pressure and temperature, these contrails will lead to cirrus clouds, not the natural ones, but the so-called cirrus contrails. And these are long-lasting clouds that modify the radiative budget. And even though these happen, not very often, once there is an outbreak of such high altitude cirrus contrails, it does modify the radiative budget in a way that it will heat or warm the atmosphere. So, and this is basically the result that is being summarized here in this table. So if you don't account for these contrail cirrus, you have a certain climate forcing, which is measured in milliwatt per square meters of the Earth's surface. And if you account for this, it's more than 2/3. You have a very strong impact. So just remember, there's more than just the CO2. There are also those non-CO2 effects, mostly due to contrails, and I'll explain where they come from, these contrails. Okay, so now I'm going to try to define what is SAF, Sustainable Aviation Fuel. It's a synthetic renewable aviation fuel that meets both sustainability criteria as well as technical criteria. And this is very important, and I'll go deeper into the details of the technical criteria. You can have various feedstocks to produce these different types of SAF, but what's important is that from a life cycle perspective, you have a reduction of CO2 emissions because it's not a fossil feedstock, it's a renewable feedstock. But there's much more criteria than just being renewable. There's very many criteria in terms of their environmental impact, the social aspect, also the economic aspect has to go towards a circular economy. And definitely social aspects. They can be produced by, children in the savannah. That doesn't go. So, and it's not a pure Cartesian definition, like something is renewable, you know that, okay, it will regrow, that is renewable. That's a Cartesian definition. Here, there's many aspects. So it's an evolutive definition, but it's very important to take that into account. So that's the definition from a life cycle perspective. Now, from a technical perspective, this is quite a complex slide, so I'm going to try to go through it. Before you put a new fuel in your aircraft, you as a passenger, but also you as a future OEM employee, working on those aircraft fuel systems or engine, you really want to make sure that that type of fuel, that the molecules that are going to come in are compatible with the system and do not put the passenger in danger or guarantee the airworthiness of your system. So before you bring a new type of fuel, you want to do a screening or pre-screening process. It's called a pre-screening process because the next step is the so-called approval process. It's an ASTM process that is quite long, quite costly, and you can't just go randomly. You need to make sure that you as a producer came up with a molecule that will be produced in a continuous way. You'll always have this composition, and you want to make sure that it is compatible with the fuel and the entire aircraft system. So you have different tiers, different steps in this approval process, checking different properties, different sub-processes occurring in the aircraft. Very long, very costly, as I said, and in the end, if you succeed after, let's say, 2 to 3 years, your fuel, your SAF, is approved and can be used in the form of a blend. But before that, you have the screening. I'll describe more about it. So that's very helpful because sometimes small producers can't really know what's out there, all the specifications that you need to fulfill as a jet fuel. So we come into play as experts and tell them, okay, if you can produce 500 milliliters of that product, we can tell you if it has a chance, if it stands a chance to go through the approval process. And this screening process, we're trying to use a lot of fast methods. So there's definitely some analytics. So you want to know what's in the fuel, but there's also a lot of models to try to assess what kind of fuel. And this is where you see now the big picture. You want to bring SAFs on the market, but you want to make sure it's safe. And so you want to use methods, different methods and tools from the digital world, from the CFD, to assess this fuel and then analyze it and then give your expert's view on that new candidate and say, yes, it is a possible SAF candidate. And then it goes through this approval process. Okay, so here are some examples. There were so-called 8 pathways that are now included as SAF, as alternative fuels approved for use in commercial aviation. I won't list them all, but they all come from different feedstock, different processes, chemical, thermochemical, biogenic processes or feedstocks. And what's important here on the right-hand side is that you can see, compared to, for us, what is the reference? Jet A1 is the jet fuel reference, fossil jet fuel reference, with all these families here listed here. So you will see this name quite often in the presentation. If you have a background in chemistry or hydrocarbon chemistry, you know them. So these are the different families, the normal alkanes, isoalkanes, the cycloalkanes, and then you have aromatics. And this is how the reference fuel looks like. And here you can see already that those different fuels that are already approved look different. Some, have a distribution of components amongst these families, but some are even just a single component or two components. So you can definitely see that this one will not have the same properties or the same, or definitely not the same composition, and it will affect very differently the different sub-processes occurring in the combustion chamber or in the fuel system. Okay, so how do we get from a fuel sample, like a liquid fuel, to this type of information, which is very useful? And this is what I'm going to try to present. You get the fuel sample, and you want to characterize that sample from its composition perspective, and then later on, the different physical and chemical properties. So here we use analytics, different standard or sometimes non-standard instruments to try to assess really what's in the fuel. Here it's called GC by GC, and it's coupled to MS. So GC is gas chromatography. It's 2D, so that's the type of result. And then you couple it with mass spectroscopy to try to see what is exactly that molecule that I just was able to identify. And then what for us as modelers, you need to transform that information into a quantitative composition. So here, a presentation of a detailed quantitative fuel composition for a reference jet A1. And you see the different families that I mentioned before, and what kind of species are in different families. So jet fuel, usually you have a carbon number between C8 all the way to C maximum 16. So this is what you see here, the carbon number and then the distribution of those single components within that family. And then that for all the different families. So another very important aspect when you characterize hydrocarbons is the so-called C to H ratio. So how much hydrogen atoms you have with respect to carbon atoms. So next step, you want to know the thermophysical properties of your fuel. And you have constants that characterize any kind of molecule species. So you want to use these constants and then plug them into a model to try to derive, let's say, a density, a viscosity, heat conductivity, and so on. All these properties are extremely important to first assess the fuel and later to maybe plug this fuel into your CFD code and see what will be the output. But you need to know those properties. So there's a whole modeling aspect behind it. Here, a list of these constants that characterize any species, and then often we deal with real fuel. So it's not just one molecule, it's a mix of hundreds of molecules. So you need a mixing rule. So you combine the property of each species, the proper mixing rule, and believe me, it's not just a simple average or weight, weight-based average. It's very nonlinear often if you look at viscosities or surface tensions or others. So this is one aspect. Then one example here for different fuels that were used actually in real for the density. So here it's the density plotted as the function of the temperature. And here for one temperature, 15 degrees C's, I gave the result from an analysis. So each refinery, when they produce a fuel, they need to give a so-called certificate of analysis where all those properties are listed. So you list them, and you have here for all the fuels that we use, the density. Now, if later you want to understand, by using these different fuels, I did observe different performance or different emissions, I need to know where it's coming from. So obviously it's coming from a different composition, and then it implies different properties. So here I see different densities. And if I want to model that, I need to be able to find physical properties model that capture these differences. So not only do you want a small error when you model the density, here with the model so-called from Constantino and Gani, but you will also need to find the same ranking. So here, this is the highest with reference 1 jet A1, and then it goes 2, 3, 4, 5, 6, and so on. And this ranking in your certificate of analysis, you want the same one from your model so that in the end, you have this difference that you capture in your model. It's very important. And you see that the differences are not that big. But here for the density, we succeeded, we have the same ranking. Now, if I look at the viscosity or the kinematic viscosity, we used a different model. It's extremely difficult to model and not in the high temperature area because they all collapse to almost a single value, but in the low temperature areas. Why do we look at -20 or even -40 degrees Celsius? Because your fuel will undergo very strong temperature gradients. Whether you land, let's say in Canada, where it sometimes is very cold and you have -30 outside, you want to make sure that your fuel stays not only liquid, but has still a low or high enough viscosity so that it doesn't become like a toothpaste. And so this is a criteria. This is a very important specification in your fuel. And you want to make sure that at -20 degrees Celsius, it stays here. You see the specification stated by ASTM. It cannot be above this value. So here we're okay, but you can see that the models do not perform that great as opposed to the density. And especially the ranking is not the same. So physics-based model here in that case for very complex mixtures, that's the best we can get so far. So this is why we had to switch to machine learning models. And this is why I'm trying also to present this aspect in our work or in the modeling, is that we also use machine learning models. So I know it's en vogue, it's very powerful, but you need lots of things. First, you need a very large database of a very good quality. So this is what we've been gathering in the past 10 years. Lots of certificate of analysis, but not just certificate of analysis, also results from GC by GC, these plots that I showed you where you have the detailed composition. Once you have this data, you can train your models. So it could be GPR, so Gaussian progress regression type of models, or Monte Carlo dropout type of neural network models. So you train your data, you take some part of your data out, and then you test your model, and it's very powerful, and it gave us very good results. Here, as an example, again, the density in green, you have the physical model, and it's good. But you see that machine learning models are excellent in that area. And what we wanted is also for viscosity. And here, where the physical models were not that great, the machine learning models perform much better. Now, the caveat is sometimes you need to extrapolate. Sometimes you have your model or your data that's within a certain temperature range, and then you find yourself outside of this temperature range. That's where the physics-based model actually perform very good. And sometimes the machine learning model is not that great because they were not trained for that area. So this is why, and that's a strong message for you, to always keep both. I know data science and machine learning is a big topic right now. So it's very important to be knowledgeable in that area, but I would highly recommend to also keep the physics on your side and always check with the physics. Okay, so these different models were plugged into one of the methods and tool I wanted to present, which is SimFuel. So it's really a combination of different aspects. I already mentioned the database, so big data, very important. This is really the new gold, or the new black oil of today's is data. Wherever you see data, you'll have a business behind it. I won't talk about social media, but I guess you're much more aware of me of that. So it's important to have a lot of data and a lot of good data. But don't forget, always have the human in the loop to try to understand what is the outcome of this model or of this analysis. And so we combine this with high fidelity simulation also to perform these assessments and analysis. And sometimes we combine it with partners, because you will see our focus is more on the combustion system, but that's not all. In an aircraft, there's also the fuel system, there's the fuel storage, every aspect is important. So we have experts in other areas, and we have distributed models. We can all combine them to, in the end, assess this fuel. This is one example of what this platform can do. So this is we developed a dashboard. So obviously you have scientists working behind it, and they work directly with scripts and Jupyter notebooks and so on, Python scripted different models and and notebooks. But more and more, we want to give the opportunity to industry or to external users to use this assessment platform. And this is the kind of interface. So it's a dashboard that you can use. You plug in your composition. So you come with your own composition. Here it's a Jet A1, so the classical fuel. You have here a certain representation of your composition. And then, very important, to assess these types of fuel, you can compare your reference fuel with what's existing. So here, the different families, mass percent of each family. And here, this kind of box plot here shows the result from the large database on jet fuel. So you have a median value and then the different quartiles, and you see that the Jet A1 that we selected is very close to this median value. But also as an information, you have all the existing alternative fuels already. So how they look compared to, let's say, a conventional fossil-based Jet A1. And you could, once you develop a certain expertise, you see immediately if it's within what you expect or outside, and then you can give a feedback. And the same here for the properties here, the kinematic viscosity. And here also the specifications for just a second. Yeah, the specifications for a HEFA SPK. So it's a hydrotreated esters and fatty acid. It's a type of SAF. And you can see that it is within the specification, but it has to be blended with Jet A1 to come into the jet fuel specification. So this is just an example of how the type of results you can get. Now, the other types of tools, obviously, I think this is also an area where you're strong, is we have CFD tools. So we have CFD tools for reacting flows on the gaseous phase. I won't go through all the details, but what's important here, so it's we can use it in three-dimensional grids, so computational domains. It's based on finite volume discretization, and it's based on unstructured grid, which is interesting for us because often these combustion systems and the different combustors are complex geometries. So this is important to capture all these details. Here's some information about the solvers. What I'd like here to underline is the fact that we have a solver for stiff chemistry. So what we simulate are reacting flows, and under very a wide range of conditions. And sometimes, you know, the chemistry is hard to solve with numerical methods. So you need these type of under relaxing schemes to make sure that it's not going to diverge or just stop. It's very very hard. The other solver that we have is for the spray. So the fuel in aeronautics is at least still currently, maybe in the future it will be gaseous, but currently it is still liquid. And so you bring it as a liquid, you transport it as a liquid, but then you inject it, atomize it, vaporize it, and then it reacts in the gas phase. So you need a solver for this discontinuous phase, the liquid, or the dispersed phase, and that's called SPRAYSIM. So for the continuous phase, it was THETA, and then we have SPRAYSIM. So yeah, it solves the spray. It tracks mathematical particles that represent the droplets, and you have the different models for the liquid phase, and especially for the vaporization of the liquid phase. And here, very importantly, because we're dealing with real fuels, complex compositions and mixtures, as I presented earlier. So that's why we have a multi-component vaporization model. Okay, so short break. Here we are. I presented the context, the different methods. Now I'll try to describe more precisely the problem at hand and show that it's a multi-scale, multi-physics problem. First, maybe because I know, I can tell, you're kind of skeptical and say, what are those non-CO₂ effects and contrails that I see in the sky? How come they form and then they can really change the climate or force the climate? So I'll try to explain briefly how these contrails are formed, and then how under certain conditions they become long-lasting cirrus clouds. So, and here is the relationship between what I've described about the fuel, the reacting flow in the combustion chamber, and the environment. So you have the product of your combustion, CO₂ and water, but you also have pollutants and some intermediate species that do form soot. Soot are those black particles or black carbon particles that come out of any combustion engine. You see it on the road, but it's also in the sky. And so they're formed and they exit the engine here. So this is the engine. You have the plume and you have soot particles. So it's the solid particles, but you also have volatile particles. So you have to remember it comes out hot, but then these volatile particles will tend, because it's very cold in these altitudes, so they will condense into water, and then all this mixture will form ice crystals. Why? Because the condensation of the water that's both coming out of the engine, but also entrained, there's water in the atmosphere, and so it is entrained into this plume. This water condenses and nucleates on these nucleation sites, and that's when it becomes ice crystals. And under certain conditions, and it's the so-called Schmidt-Appelmann threshold in terms of temperature and humidity, these will stay and become cirrus clouds, just like a natural cloud under these altitudes, except that it was anthropologic. It was anthropogenic, made by human. So that's the concept behind it. That's the concept behind it. Now, there are codes, and there's a whole research area related to plume physics and the impact in the atmosphere. I just wanted to mention it because it's also another area. Plus, it was important to show what is the connection between the fuel properties, the combustion process, the plume, so what comes out of the engine, and then the environment. So this is the link. At the Institute, our focus is more on what is going on within the combustion chamber and in the near field of the combustor. So you have fuel injection here. And from a bulk liquid phase, you want to make as many small droplets as possible so that they go into the so-called primary zone of your combustor, they evaporate, and then they burn as uniform and nicely as possible. That's not always the case. So we need to look at atomization processes. We need to look at how the droplets are transported and how they interact with the turbulence. We need to look at how they evaporate and how the different fuels evaporate. Is it beneficial or not to your primary zone and to your combustion process? And then how the different fuels produce pollutants and different emissions. So this is not just at the DLR. It was developed or let's say put in this kind of theory by the AIAA. But it's a very interesting way to try to formalize a little bit the work that we're doing in research. So you're starting with a complex problem. For example, what is happening, what is occurring in a combustion chamber under realistic condition, and then you break it down into subsystems. So just focus on the primary zone, not on the whole combustion chamber, or focus on the cooling, or you have subsystems, and then you divide it into physical or chemical sub-processes, and then it becomes what we call a unit problem. let's say, what is the laminar flame velocity of a fuel, of a gaseous fuel, or what is the atomization or the evaporation. And I'm going to focus on a few of these. Once you understand the fuel impact on any of these fuel-dependent subprocesses, and you put it together in the code in a coupled way, then you can understand how they interact and understand then what was happening in the in the real life at the exit or in the plume of an engine. So this is the strategy behind it. And we use the tools that I presented to look at these different sub-processes. So I'm going to show a few examples. Here it's atomization. You have different types of atomizers. Some here are quite a canonical problem, but it's very interesting to understand so that then you can apply it to a relevant technology, such as here the pressure swirl atomizer or pre-filming air blast atomization system. But in most or in all atomization problems, it comes down to these three liquid fuel properties: the liquid density, the liquid surface tension, and the liquid viscosity. This is why I presented earlier on all the models behind, behind trying to capture the fuel's effect on these specific properties. Now, how we do it, I mean, to be honest, this is still an open problem: atomization, primary breakup, and so on. However, you need to do something in your code. So often it comes down to what is the best correlation to implement in your code. And whether I'm talking about atomization, or you will see in many other problems, you don't have the final, very accurate model. You need to pick a correlation that is valid for the range of conditions that you've selected. So here for pressure swirl atomizer, the simplex atomizer, there were some measurements, and then there's a correlation that we've used, and that works in some cases. And here, just as an example to give you a feeling about what is the impact of different fuels on such an atomizer. So you have different pressure or mass flow condition that goes through this injector. There's a measurement of a characteristic droplet diameter. Here it's in micrometers. That's the reference, and then the model. And you see that's the deviation. And you see that for most of the cases, it's well captured. And so that was for jet A1. Now, if you use different fuels, so this is a fully synthetic jet fuel. This is a HEFA, I talked about it before. And this is a blend between HEFA and the reference fuel. And here you see the difference, or in percent. So you see it's not negligible. So already a different fuel will generate different droplets. So already you have an effect on your process. Different atomizers. Here it's air blast, different models. Here it's what we call the semi-empirical model. I think you had not too long ago a presentation from Jolon Estivales, and he's looking at these problems of interface tracking for modeling atomization. So we also have these models, but I wanted to present also some semi-empirical models here. So you need to capture the instabilities on this film, and then the formation of this bag here. So you have an airflow flowing above, generating this instability, producing these bags, and also these ligaments. Then the ligaments disintegrate through the Rayleigh-Taylor instability. So all this needs to be captured with semi-empirical models. And once you develop this model and you make sure that it is fuel dependent, so that the different properties listed here are captured in your model, then you see, do you really capture this fuel dependency? So here it was used with different solvents, and they have different properties listed here. And what's important is not just to capture one average diameter, but the distribution of droplets that are coming out of these types of injectors. And you see here that the model captures these differences. It's not perfect, but believe me, it's already very good, knowing how complex the atomization problem is. So that was just an example. The second unit problem I wanted to present is evaporation, because it is extremely important. Some fuels evaporate quite fast, so we say they're very volatile, and some others, like bunker type of fuel that you use in big ships, they at room temperature they don't evaporate; they're almost solid. So that's why you need to capture that. So again, you think of a unit test case, of an experiment that has conditions that are very representative of the real case, but where you can isolate your problem. So here we isolate the droplet, we set the single droplets in a temperature and a flow environment that is similar to what such droplets would experience in a combustion chamber, and then you measure the evaporation rate. Now, another method that I wanted to mention is uncertainty quantification, UQ, because often you will see results where you have, I don't know, I don't have it here, but you have the experimental points that are, dots, and then the curve, which is the simulation. But whether you look at the experiment or the simulation, you need to capture these uncertainties because it's never set to a 0.001% accuracy, whether you look at your flow velocity, your temperature, your droplet velocity or the droplet diameter. So once you implement these uncertainties into your problem, into your model, you can then see what was the impact, and then it gives better confidence into your model. So this is basically what this diagram is showing here. We're using the tools that are presented. We're coupling them with Dakota, which is a tool developed by Sandia National Labs in the US, and where you're able to really give many different inputs in terms of boundary conditions and see what was the effect of this variation in the input on your results. So another aspect that I wanted to present is, the evaporation model. So if your fuel has more than 100 species, it will be very costly in terms of CPU time to track all those 100 species. So the idea is, instead of using discrete components, to use a distribution function, and you actually transport the probability density function of that distribution. So this is what's explained here. It comes down to, instead of transporting in your problem, in your simulation, hundreds of species, which means hundreds of equations to solve, you basically solve two parameters that define these curves here, these distribution functions. And you have a mapping between what characterizes this function, so the mean and the standard deviation, and what characterizes this function here, alpha, beta, and the origin, gamma. I won't go into the details, but just so you know, it does simplify the problem. You lose a little bit in the accuracy, but you can actually compute complex fuels. Here, the result now on the left-hand side for the evaporation problem for single components, and on the right-hand side for multi-component fuels. And like I said, instead of having just the experimental points and the curve showing the simulation, you have now a whole area, because we looked at the impact of different boundary conditions on our result. And you could see that it fits pretty well for the single components. For the multi-components, to, let's say, 60–70% of the evaporation time, it is very good. And then there are some discrepancies, probably related to the fact that we model our discrete distribution with a continuous distribution, and that towards the end, the properties are not that well matched. But still, it is very good, and these are different shields. So A1 was a reference jet A1, B1 is a HEFA, and then you have complex fuels with high or very low volatility. Okay, so we looked at atomization, very important subprocess, evaporation, another one. Both are important for the so-called fuel placement in the combustion chamber. And now we need to look at the reaction. How do these fuels react in the combustion chamber? Again, we simplify the problem of just looking at fuel oxidation, and there are different ways. If you want to look at the ignition delay time, how fast, under what condition will your fuel ignite? So you can do that by using shock tubes. We have that at the institute. You want to look at the flame velocity. How fast will the flame progress in a gaseous environment? Very important. You can naturally or feel that hydrogen will burn very fast, whereas maybe methane or others don't burn as fast. And then you want to look at the different species that are formed, not CO2 and water, but the intermediate species that are formed during a reaction. So we have shock tubes, we have laminar flame burners here, and we have flow reactors to look at the different species. And these first give very important information, but also the base for developing models for the chemical kinetics. Again, I can't go into the details here, but these models are then implemented in the CFD. Here, just an example from the flow reactor. For different fuels here, so you've seen these names, reference 1, reference 2, are two different jet A1, so the fossil-based standard conventional jet fuel, and then semi-synthetic jet fuel, fully synthetic jet fuel, different types. And you can see already that these fuels, when they burn, they produce intermediate species. And one is important is benzene, C6H6. It's not in the molecule initially, it's produced during the reaction. And these are so-called soot precursors. So the more of these intermediate species you have for a specific fuel, the more soot you can expect at the exhaust of your engine. And so here you have kind of a ranking of these different fuels. For the different, so here for benzene and different types of aromatics molecules. So very important to look at what is the impact of fuel in a reaction and what type of intermediate species are produced. And these, then you need to capture it also in your model to then understand under what condition, what soot precursor will be formed, and then you'll understand why was there more soot with this fuel than this other fuel. Okay, now if we put all this together into a complex problem, not yet the whole aircraft, but already a complex problem of a high pressure single sector rig. Single sector means that you have only one combustor, whereas in an aircraft engine, usually you have many, from let's say 8 to 24 sometimes, huge engines. So you look at a single sector, but under realistic conditions in terms of pressure, mass flow, liquid mass flow, air mass flow. And in the lab, you can observe here. So this is why you have windows. You can observe with video, or you can perform laser diagnostics to try to understand what is going on in this flame. And here, one aspect is the so-called OH chemiluminescence. So it's basically to see where is the reaction zone. So you can imagine your fuel was coming here. There's a very complex flow. It's called a swirling flow that is occurring to stabilize the flame. And this is a visualization of the reaction zone for 6 bar. So it's non-negligible. Modern aircraft Patrick. Go all the way. Sorry, what?
10 minutes.
Excellent. Thank you. Yes. So relevant conditions. The phi determines the stoichiometry, so the mixture between the fuel and the air. So this is close to what we call normal stoichiometry. So it would be like a cruise. And the different fuels. So the reference, the fully synthetic, the semi-synthetic, and here is a pure SPK. So the message here is you can see the form of the reaction zone, and for the different fuels, it doesn't really change. So that's good news. This combustor was so well designed that the fuels that are quite different still lead to very similar flame. And this is what we also captured in the simulation. We simulated a very similar type of swirling flames, and you could see here the reaction zone. It's not the same, but it's similar. I just wanted to show the difference. And you don't see any difference in the reaction zone. So that's important. However, now if you look at the soot formation, so here it's the soot really from a visual viewpoint. Soot is basically this red orange, even in a candle flame. The orange part of the candle is actually the radiation coming from the soot. And if it was blue, like your gas burner when you cook, it's from natural gas. There is almost no soot. So here, if you use a reference fuel, you see a lot of soot, and this is here on the plot, a lot of soot for the reference fuel. If you use a semi-synthetic or fully synthetic jet fuel, there are less aromatic components in these fuels. Very important. Less aromatic components means less soot, and this is exactly what you see, less soot from the visual aspect, but also this kind of global measurement. And now if you use SPK, you see not much soot. I'm not saying that there won't be any soot coming out of an engine, but at least in this experiment, there's much less. And this is now, if we look at the soot precursors, so the benzene, remember that molecule, that green molecule? Here I plotted the concentration. You see that you have a much higher concentration for jet A1 than for the pure SPK. You still have some, but it will be much less. And so it means that you will probably have less soot being produced by this type of fuel. Okay, now a very important slide, we're almost to the end, is try to summarize everything that I presented. And you could see that we have different ways of assessing the fuel, looking at the composition of the fuel, the different compositions that we saw, looking at the physical and chemical properties, looking at the combustion of these fuels, but in a very accurate and specific experiment, looking at these intermediate species that are produced during the combustion of these fuels. And then you increase the complexity. We looked at some burners. Here it's an atmospheric burner that we also simulate with LES. I didn't present it because we didn't do a fuel variation, but it's very interesting to understand what's going on in this flow here. And then you increase the complexity all the way to being outside during these measurement campaigns. And this is what I'm going to try to present. So once you understand the fuel impact on the properties, the combustion, the soot formation, and this into a complex flow, then you can really understand what is going on in the engine and then in the plume. And so you understand then the results from such measurements. And so this is what I call the real fuel application. So we did perform several measurement campaigns from 2014 all the way to 2021. Some were actually even with NRC Canada. So we have a scientist from Canada working with us specifically on ground measurements. So the point here is, even as someone working on génie mécanique or simulation, CFD, once you understand all these processes, then you can really be part of these also outside experiments, the real life measurements. I was in charge of organizing these measurement campaigns because you understand what is the fuel's impact on what's going on in the engine, on the emissions, and on the climate impact. So here, by using these types of fuel that I presented, the SAFs, the HEFA, for example, you reduce the soot emission. And reducing soot emission means reducing the ice crystal formation in the wake here in the contrails, which means reducing the climate impact. So we want to push for these types of fuel by understanding what's going on if you change the composition, if you design the composition. So here in this measurement campaign, after this one where we gathered a lot of data, we understood, yes, you need to reduce the amount of aromatics in your fuel, but also the type of aromatics, the de-aromatics. And this is what we did. So here the result is by using only 30% of HEFA, we got the same soot reduction as by using 50% of HEFA. So it means if you design very well your fuel, because they're very expensive, by using a little bit less of fuel, you can still get to the same result in terms of soot reduction. Okay, so that was the real life experience. And now I'm at the end, and I thank you very, very much for your attention, and I'll be happy to answer not too difficult questions, please, but I'll be happy to answer questions. Thank you.